Okay, so let's start off this last section here in the circuits unit. This set of notes should not take too long. I know I didn't give you a lot of chance to ask questions in the other classes, so I want to try and go through this quickly so you can ask lots of questions, because I'm sure there are quite a bit. This is the last lesson. Just this one is going to be the videos. The other ones are not recorded.
Tomorrow we won't have video?
Tomorrow's review already. No, you should have been writing it down as you went along. So it's quite funny actually, the amount of students who have complained to me about why I'm not recording videos that were done on Zoom. Do you remember 2 years ago, back before COVID, how many teachers recorded lessons? Nobody. Now all of a sudden it's like an expectation that lessons are recorded. Exactly. So now when everyone's in class, there's no reason for me to record it. You have to actually pay attention during class time. Yeah, that one's all videos no matter what. But those are good videos, not like these ones. And they're short. They're like under 20 minutes each or something. Hopefully. Okay, so today we're learning about something that's called electromotive force. This is not actually a force. It is something that was thought to be a force at some point. So electromotive force is actually still a voltage. It's a type of power supply, basically. So with a circuit, remember with a circuit, you need to have a power supply and you need to have a complete circuit. But what they determined is if you just have a power supply by itself and it's not connected to anything, it still has some amount of voltage. And as soon as you connect it to something and create a current, that voltage decreases. So the amount of voltage in a power supply without attaching anything, this is what the electromotive force is. And that's what we're going to be talking about today. So, for example, car batteries, if they're not connected to anything, it has an EMF of 12 voltage. As soon as you connect it up to a circuit, that's going to decrease. We'll get to that. We're going to get to it. It's not because of that. So with a lithium battery, so lots of like the AAA, AA's, yeah, stuff like that, it has an EMF of 1.5 volts. So again, if it's not connected to anything, that's going to be your voltage. But as soon as you attach your battery to something and you've got the current flowing, what happens is there's actually an internal resistance in the battery. And if you remember, if current flows through a resistor, you lose voltage. So essentially the main thing that tells us that we're going to have a smaller amount through the terminal is, where is it? Here it is. You have some internal resistance. So the terminal voltage, remember terminal voltage is what is the voltage between the two ends of my battery, and the EMF are two different things. I'll explain, once you see a diagram and you see an equation, it'll make a little bit more sense, I think. But essentially what you need to recognize is this. Electromotive force is what's the voltage on a battery that is not connected to anything. That's not connected to anything. So in the cupboards at the back, I have a bunch of batteries. They have an electromotive force because they're not connected to anything. So here is the equation for this. So let me explain what the variables are here. So we've got voltage. This is the terminal voltage. You typically won't see this as V terminal like this. You'll see this written as VT. This is posted up online. You don't need to take pictures. Capital. So V total, V terminal, same thing. So the voltage that's on either end of your battery is going to be your total voltage. This is equal to, so this epsilon, so just the curvy E, this is your EMF, electromotive force. And this part here, this is my internal voltage drop. So because there's voltage running through the battery, I lose voltage because there's a resistance inside of the battery. No matter what your battery is, it's not 100% efficient. You should recognize that from a different unit. You lose some energy when you are running the battery. So you can see here, if I do not connect my battery to a circuit, my current is 0. Therefore, the V terminal is just the EMF. But that's only if I'm not connected to anything. I know it's really hard to get back into the routine of fully paying attention while a lesson is going on. You can't carry on side conversations. You can't be texting. You can't be checking your phone. So this is the equation that you've got. V terminal is equal to all this. Yeah, you guys are still writing. I'll hold that for a sec. So you might be thinking, how do I know when I use this equation with an EMF, and how do I know in a question that it's just dealing with the V terminal and not the EMF? Or how could the EMF? No, this is with a circuit. I'll show you in a sec. We'll get to something where you'll see where this works. Because where this comes into play is I can deal with the internal with this equation. I can deal with the external, like outside of the battery, with V terminal equals I total times R total.
There's another equation.
No, not another equation. I'm just going to connect this to what you've learned already. So let me show you what this looks like in a diagram. Now I need to pull up my picture so it looks nice. You are never going to draw the diagram unless you really want to. If I give you the diagram, there's going to be no marks for you to draw it. If I give you I cannot give you a question that you don't have the diagram. Okay. So here is what you will see if you are dealing with an EMF equation. So the nice thing is, on a circuit diagram, if you see the dotted box, you're dealing with EMF. If there is no dotted box, it's just a normal circuit like you've already seen. So it's really easy to see the difference between them. So that shouldn't hopefully be a difficulty for you.
Is that a different thought from like the wording of the question, but like
there will be some cases where, like I'll show you in the next couple examples, where you see just words, and then it's pretty obvious. It's not going to be too bad. So what is all this stuff that's on here? So this dotted box is my battery. Battery, yeah. Power supply. So this is your cell that's inside the battery. This, if it's inside of the dotted box, this is your EMF. The electromotive force is inside of the battery, just like your internal resistance is inside the battery. There is no actual resistor that's pushed inside of the battery. This is just due to the physical nature of the battery. Anything that's on the outside, so this resistor is outside the battery, these are capital R's. Internal resistance is lowercase. Outside of the battery is capital. Yeah. And if I were to try and figure out where is V total or V terminal, it is from this side of the battery to this side of the battery. So if I were to connect up a voltmeter here, this would give me, just a sec. This is V terminal, V total, whatever you want to call it. From one end of the battery to the other is V terminal. So you can see how I can get two different equations here. So I've got Vt can first of all equal the EMF minus capital IR, because capital I, the current's running through the whole thing's the same. There's no paths that you can diverge off of. And I can also have V total is I, which is I total, times R total. So you can see how I can combine everything you've learned before with this, and now just attach this. Depending on what you're given, if I told you what the R total is and what the current is, I could ask you for EMF. Or if I gave you, what else could I give you? I could give you the EMF, the two resistance values, and you can solve for current. So it just so that you know, because often students get confused, you can't use these two together. I want to point out that that's for sure, you can. So many of you have probably dealt with cases where your batteries go dead. AAA batteries, AA batteries, stuff like that. The reason why batteries die is your internal voltage meets the EMF. So as your battery gets older, this value increases. And once it reaches this, then your battery's dead. Yes. So your EMF stays the same. It's still, that's not changing, but your internal voltage is taking away all the energy. Not possible. No. That's like saying what happens, oh no, that case doesn't work. So if I have my water bottle here on the desk, let's imagine I have that. If I push this with a force applied that's smaller than the force of friction, what happens? Nothing. Same thing here. You can't have this one go bigger because it just reaches this and then it's stopped. I mean, it could get bigger, but you're not going to have a negative terminal voltage. Yes. Yes, batteries push out protons. That's right. So, maybe. So here is how a question will be phrased if you're looking for EMF or you're given that. So if you have a this many volt battery, this many volt power supply, this many volt whatever, that's your EMF. So that's how that's going to be phrased. And you will have a combination of different things. Either you can talk about internal resistance, you can talk about a battery being depleted, you can talk about decrease in EMF. There's many different things to indicate specifically that you've got EMF. Yeah, this is your EMF. So EMF is 12, then you have the current and the internal resistance. Oh, this is the unit. Just like your amps, this is, yeah. Yeah, I don't normally put, don't worry about this. These are just the units.
What are you solving for? The velocity term. How did you tell the difference between the initial resistance and
So this one says internal resistance of this.
it's the first day back, right?
Yes, it is the first day back. You had a long 5-day holiday, which I'm sure you got very little sleep on.
No, I don't. I'm still waiting for myself. Is there a difference between capital R and
Yes, the capital R is an external resistance, so a resistor outside the battery. Lowercase r is internal. Yeah, so they're two different things. Any questions on this? So just to make things more complicated, we also have an equation that looks like this. What's different? Now I've got a plus. So the only case you're going to have a plus is when you're recharging a battery. If I want to charge a battery, I need to have a bigger terminal voltage to cause the current to flow backwards, which is what you were saying. So if you have a car battery that's died on you, which happens way too often, you need to supply a voltage to your car battery big enough to get it to go. Yeah, so you jump setting your car. And that's going to be to charge your whatever. So
that's why they put like the thing on the plus and minus. So there's any voltage and output.
yeah, so you're causing
You have a charger?
what kind of charger?
Because this doesn't have some.
Is it the same kind as an iPhone?
No.
Then I don't have a charger for that. That's the only one I got. Speaking of recharging batteries, this should be a common occurrence to basically all of you. Like Ziad is proving at this point. Ziad, thank you for providing such a good example to what we're talking about here today. Yeah. So this is going to be one very specific case. Anytime you see something being charged, use the plus. That's the only difference. So again, yeah, if something is charging, you plus.
Because it's not losing voltage, it's gaining.
Yeah. You need to supply a bigger terminal voltage to charge your car or the battery, whatever you've got. So again, whenever it says this many volt something, EMF. Your alternator's supplying this, so this is your V terminal. That's what you're applying to your car battery, and then you're given the internal resistance. So these are the two things that you need to notice. Anytime it's being charged, plus.
How did you do that? What's the other problem with that?
Subtract EMF, divide by R.
Divide by R or by R?
Divide by just R, because you're solving for I.
Yeah, because there's two different variables. I
Then it's a normal circuit. Your battery's just being used. Yeah, you can think of it like what's happening to your battery. You want your battery to gain power? Plus. Is your battery losing power? Minus. Not too difficult to remember. All right, that's it for this lesson.